Welcome to another AP Chemistry General Chemistry video. I'm Jeremy Krug. In this series, we're learning about weak acids and weak bases in this complete AP Chemistry course on YouTube. Now, in our last video, we focused on weak acids. This time, though, we're focusing on weak bases and how those work. Now, when we look at some examples of weak bases, we can think of things like a pyridine or ammonia. That's a very common one that comes up. We could talk about urea, or we could have hydrazine that comes up here, or aniline. Now, as we look at these weak bases, you might notice that they have something all in common. They all have hydrogen and nitrogen in their formulas. Now, generally speaking, in the weak bases that we deal with in general chemistry and in AP chemistry, almost all of these Bronsted-Lowry weak bases that we're going to deal with are going to have that nitrogen atom in there. So if you see a covalently bonded formula that has a nitrogen and a hydrogen in it, there's a good chance that it's going to be a weak base. And so these are some of the most common weak bases that we deal with in this course in AP Chemistry and in General Chemistry, but there are some others, and be aware that those could pop up as well. Now, how do these problems work? Well, let's try an example. Let's consider a 0.40 molar solution of ammonia. Now, this base has a Kb of 1.8 times 10 to the negative fifth. Write the base dissociation reaction for ammonia. Now, you might notice we have a Kb in here this time. In the last video, we had weak acids that had a Ka. Well, B would work for bases, wouldn't it? So we're adding to our alphabet of equilibrium constants. We had Kc, Kp, Ksp, Kw, we had Ka. Now we're adding Kb into this. So let's write the base dissociation reaction for ammonia. Well, we start out writing the NH3, of course, and it's going to react with water. Now, since a base is going to be a proton acceptor, that means that one of the products should always be the conjugate acid, right? So we're going to add an H plus onto this and make one of the products NH4 plus, so just like that. And then since it's a base, we would expect to have hydroxide, wouldn't we? So those are the two products in this base dissociation reaction. And by the way, hydroxide is just, of course, the conjugate base of water, isn't it? Now, let's go right into the problem here and calculate the hydroxide concentration. Now, just like with weak acids, the best way to do this is with an ice box. So I'm going to set that up on the side here. And for our initial concentration of ammonia, well, the problem says it's 0.40. So I'm going to plug that in for ammonia. And for ammonium and hydroxide ions, those will be 0. And that's all that's given to us. So that means change will have to be a minus X and plus X on the product side. So our equilibrium concentrations are 0.4 minus X, X, and X. So now we're going to plug these into the equilibrium constant expression for this reaction. So that's ammonium ion times hydroxide ion all over ammonia concentration. Don't forget, we leave out water. Water's a pure liquid. We never include liquids like water into these expressions, do we? Well, now we can just plug and chug, and the X goes in for each of those products. 0.40 minus X goes in for ammonia, and Kb was given to us as 1.8 times 10 to the negative fifth. So we can plug those in. And you might notice that Kb is a very small value, and when the equilibrium constant is small, we can ignore that negative X, can't we? So I'm going to strike that out, and I'm just going to obliterate that, so we're not going to worry about it. And now that makes our math problem a little bit easier, doesn't it? We can cross multiply. So when I cross multiply in this direction, 1.8 times 10 to the negative fifth times 0.4 is about 7.2 times 10 to the negative 6. And of course, in this direction, X times X is my X squared. So when I take the square root, I find that X equals 2.68 times 10 to the negative third. And X, as we can see, is the hydroxide ion concentration. So that's the answer to part B, isn't it? That's the hydroxide in moles per liter. Now, percent dissociation. this works just the same way as it did for a weak acid. The percent dissociation is always this number here, your X, divided by whatever it was being subtracted from, times 100. So in this case, it's going to be 2.68 times 10 to the minus third divided by 0.4 times 100. So just like that. So when I key that into my calculator, I find that the percent dissociation is about 0.67%. So very low dissociation level for here, way less than 5%, which is what you'd expect for most weak bases. Now, what about part D? It's POH. Well, remember, POH is just the negative log of the hydroxide concentration. So we're going to take the hydroxide ion that we calculated earlier, the 2.68 times 10 to the negative third, and take the negative log of that. And when we key that into our calculator, the answer is about 2.57. Now, what about the pH? Well, pH plus POH equals 14, so just subtract this number from 14, and we find that the pH is 11.43. So that makes sense. If it's a weak base, you would expect its pH to be pretty high. It has a basic pH well above 7. Now let's try one more example. In this introduction to weak bases, we're going to take a pH meter and stick it into a 0.35 molar solution of hydrazine, N2H4, and we're going to find that its pH is 10.89. So with this information, let's calculate the hydroxide ion concentration and also the Kb of this weak base. Well, if we know the pH, then we can figure out the POH, can't we? Since we're talking about a base, we need to deal in terms of POH. So we're going to subtract this from 14 and find that the POH is about 3.11. Now, if we know the POH, we can figure out the hydroxide pretty easily, right? Just take the negative antilog of this. So 10 to the negative 3.11 is going to be your hydroxide ion concentration, just like we learned in lesson 25. So we're going to plug that into our calculator and find that the hydroxide concentration is about 7.76 times 10 to the negative fourth moles per liter. Now, once we know this, I think we can figure out the other concentrations. Let's write the base dissociation reaction for this, even though it doesn't specifically ask us to. Hydrazine is N2H4, and we're going to add it to water. And we know that one of the products will be the conjugate acid, so N2H5 positive, and of course hydroxide, since this is a base. And if we know that the hydroxide concentration is 7.76 times 10 to the minus fourth, we should be able to figure out what the N2H5 positive concentration is as well, right? It's the same thing, because it's a 1-to-1 ratio. It's also 7.76 times 10 to the negative fourth. And of course, hydrazine is very close to 0.35 molar. This is a weak base, so it may be a little bit less than that, but not much less than that. So we're going to plug these numbers into the equilibrium constant expression for this reaction. Products over reactants, so it's going to be like that. We just plug those numbers in that we got up here. And when we key that into our calculator, we find that Kb indeed is a very small number. It's about 1.7 times 10 to the negative sixth. So a very small number once again. I hope you learned something about weak bases in this video. My name is Jeremy Krug. I've been teaching AP Chemistry for decades now, over 20 years. And I want you to make an A in your class. And so if you learned something, please hit that like button and subscribe if you haven't already done so. This is the entire AP Chemistry course on YouTube. I hope you hope you like this, and I hope that you join me again where we'll learn some more acid-base chemistry together.